series. This webinar series that is organized by the Committee on International Relations in Statistics and Statistics Without Border. And today it's my pleasure to introduce to you Professor Rob Dearden, who is a professor of biostatistics with a joint position in the Faculty of Veterinary Medicine and the Department of Mathematics and Statistics at the University of Calgary in Canada. And much of his recent work has been in the area of infectious disease modeling, but he's also interested in Bayesian and computational statistics, experimental design, disease surveillance methods, spatial temporal modeling, and statistical learning. He has published over 75 papers in peer-reviewed journals, has served as associate editor in a number of journals, for example, the Journal of the Royal Statistical Society Series C, and the Canadian Journal of Statistics. He is going to talk to us today about an introduction to Bayesian modeling of epidemics from population to individual level models. Rob, please, the floor is yours. But before, let me remind our participants that if you do have questions, please place them in the Q&A. And I will read the questions for Rob. It's much easier for us if you do this in the Q&A than in the chat. Okay, so please, Rob, the floor is yours.
Okay, so thanks very much, Alex, for the introduction and the invitation. It's an honor to be joining a very impressive set of speakers that you've had on this webinar series. So yeah, I'm going to talk today about epidemic models, which have obviously been in the news a little bit over the last few years. As I put this together, I found I was talking less about the Bayesian aspect than the actual models. So forgive me if you come here to get an overview of Bayesian statistics, but I'm going to spend most of my time talking about the models, and I'm going to try and give you sort of an overview of what we're trying to do with these models, but with an emphasis on simpler models, what are known as population level models, and time permitting, we'll also talk about more complex models, individual level models. Okay, and as Alex says, please feel free to put your questions in as we go along. So I'll break the talk into 3 parts, little introduction. We'll spend most of the time probably on the population level models and then a bit on the individual level models later on. Okay, so there it is, COVID-19. This is the stock image, at least from the beginning of the pandemic. And obviously this is something that's been very pressing in my field over the last few years. But we've been interested in infectious or communicable diseases for a long time. There are lots of human diseases that we're interested in, some of them very serious, like Ebola or SARS or HIV, some of them less serious, but still, you know, with some mortality attached, things like measles and influenza. And there's also a lot of interest in disease in the veterinary, in the livestock industries and the horticultural industries, mainly not to do with public health, but more to do with, well, economics for a start, but also animal welfare. And then also the models I'm going to talk about today have a lot of similarities to models that are used in ecology as well. Right? So if you're thinking about invasive species, animals or plants, the way they spread through spatially through time, that looks a lot like the way that diseases might spread spatially through time. Right? These models or extensions of these models we've also used to model things like fire spread, another thing that's obviously big in the news at the moment. And although I haven't really worked in this area, you can use these models for things like, you know, computer viruses, social means, financial market contagion. I actually went, I think about a year ago now, I went to a talk on Ponzi schemes. As part of a conference, I didn't seek this out. I was quite surprised to see that they use essentially SIR models to model Ponzi schemes. So there are, although I'm going to talk about diseases today, there are extensions outside as well. Okay, so the topic of today's talk is really going to be what we might call mechanistic models of disease transmission. Right? And I'm going to separate these from the idea of statistical models. Statistical models, in my mind, are essentially models that you take off the shelf and apply to lots of different systems, right? And they're usually mathematically derived, right? Your linear model, your GLM, and from a statistician's point of view, how we feed that through to do things like significance tests or goodness of fit tests, right? But the derivation is really mathematical if you go down to first principles. That's not the case here. The models here are built with the biological or ecological mechanisms going on in mind, right? They're quite old now. People have been using these models for over 100 years. They don't, I think I'm right in saying that they weren't designed with the idea of data analysis in mind. But obviously as a statistician, I'm very interested in how we parameterize these models, inform them via data. One of the things that's special about these models is that the parameters generally are very easily interpretable in a biological, ecological way, right? You have a parameter that represents your infectious period, how long you're infectious for. You have a parameter that might represent your contact rate or the rate at which disease transmits through the population, as opposed to a linear model where beta 1 is what happens if you increase x1 by 1 unit after accounting for all x2, x3, x4, which are really mathematical interpretations in my mind that are mapped onto the system. That's how I see it anyway. This has a big advantage if you're, especially at the beginning of, say, an epidemic or a pandemic, because the fact that these parameters are so easily interpretable means that they can generally be estimated in a piecemeal fashion. And that was certainly done at the beginning of COVID, where, mathematical biologists would go to the literature to look at estimates of the infectious period, right? And they'd go somewhere else to find estimates of the transmission rate, right? And you can estimate some of these parameters with experiments, that sort of thing as well. And then finally, the other thing that I wanted to flag up before we dive into the models is that the use of these models is generally predominantly about simulation. We want to make a prediction, a projection, right? We may want to forecast what's about to happen, or we may want to simulate and then impose some sort of control strategy to see what happens if we vaccinate 30% of the population or 50% of the population, right? Whereas the things like risk factor assessment, is my covariate significant? That tends to take a secondary position in this field. Right? It's not always, but generally. Okay. Now there are, before I carry on, just to point out what I'm not going to talk about today, and that's all the other sort of what we call disease surveillance methods for analyzing infectious disease data. And what I mean by that generally is taking, as I say, off-the-shelf statistical methods that may have been designed for other situations and applying them to disease data, right? So that might mean things like control type methods where you're observing the number of cases of a disease that's going on every day, and suddenly it takes off, and you want to identify when that change point is, right? Which in terms of disease epidemiology means when does an outbreak occur, or when does the influenza season start, right? Things like that. And then there are things like spatiotemporal disease mapping, which is essentially count regression, accounting for spatial structure or other sorts of regression, longitudinal or otherwise. Right? That's all important stuff, but it's not what I'm talking about today. Okay, so these mechanistic models, transmission models I'm talking about, there are a whole suite of them. broadly, I think you can divide them into sort of 4 different parts, right? And different people would do this in different ways, probably. But so my first one here that I'm going to talk about a lot today are these population level models. Sometimes they might be referred to as homogeneous models. And there's an underlying assumption in there that is essentially everybody's the same. You know, there's no gender effects or age effects or geographical effects about your risk of getting or passing on the disease. Everyone's the same, and everybody comes into contact with everybody else purely randomly, probably at a very low rate, but it's purely random, right? Hence the homogeneous model. And we will spend, these are very simplistic models in a way, but they're also extremely useful. And we'll spend, as I say, a fair amount of time talking about those today. Then, if you like, you can ratchet up the complexity by putting in a bit of structure, right? So say you divide your population into different subpopulations or strata. So these may be different age categories or gender or geographic regions. And essentially there you assume that predominantly within a strata, one of these homogeneous models is driving the infection, but you also allow for transmission between strata, which occurs at a different, normally much lower rate, right? So you're adding a bit of structure to your model there. If you take that a bit further, you get to the other topic that I'm going to try and address today, which is what I call individual level models. Sometimes individual based models is what they're known as. And in these models, it's more complex. It's the chances of any particular infectious individual infecting any other particular susceptible individual are going to depend upon covariates about the individuals concerned. So they may be things like age, they may be things like gender, they may be things like your spatial proximity to an infectious individual. Okay. And then there's a 4th category, which I don't really work on very much, which are also extremely popular, which I think of as being very high dimensional, highly complex versions of these models, right? An ILM might have 5, 10 parameters in it. Agent-based models may have 50, 100, 1,000 parameters in. So you're really getting in deep and trying to mimic the behavior of your population and how the disease spreads within that, right? So you might be modeling commuting patterns in a human disease or things like that. These are obviously potentially more realistic, but they're also much harder to parameterize because you've got a lot of parameters. And if you get some of those important parameters wrong, they can actually end up being quite unrealistic, right? But they're the 4 general types. And like I say, it's the population level and the individual level are really what I'm going to try and talk about today. Couple of things also about the sort of what makes these models different to general statistical models we might use. So in statistical language, it really comes down to this idea of non-independence of infection events, right? So if you think about, with these models, what we're often doing either directly or indirectly is modeling the time at which something happens. We're modeling the time of infection, the time of removal, which sounds similar to survival analysis models, right? Except in survival analysis, you have an independence assumption, right? If you're modeling cancer, lung cancer, say, after you've accounted for covariates, you know, age, lifestyle, my risk of getting lung cancer at any particular time doesn't depend on who else in the population has lung cancer. Okay? There's an independence there. That's not true with infectious diseases, right? If I am in a room with people who have influenza, my risk of getting influenza is much higher than if I'm in the same room and nobody has influenza in that room, right? So the response, if you like, affects the response of other individuals. So another way of thinking about that is you have some sort of feedback where infection drives infection. Okay. And that's one of the reasons we don't tend to use off-the-shelf statistical models we use these more mechanistic models. Okay. And then one final point, I am going to show you a model in a minute. One final point is that a lot of the modeling that's done in infectious disease work is done in continuous time, and I do that. Here I'm going to use discrete time models. Okay, so my t is going to be an integer. We're sort of, if you like, building our model to follow the data in some sense. It comes in daily or weekly. The actual process is obviously continuous, right? There's a time of day at which you get infected, but we're going to be ignoring that in these models. But all of what I'm going to talk about today can be done with continuous time as well. Okay. Okay. So I wonder, I've actually hidden my panel there, but I wonder if there are any questions. I can't see anything there.
No questions, Rob.
Oh, okay.
You may go ahead.
So I will move on. Just gonna, there we go. All right, so let's look at a population level model. So I'm going to talk about a model that you've probably heard of, which is the SIR model. It is essentially the simplest well, no, that's not quite true. I was going to say the simplest non-trivial. It's one of the simpler non-trivial models. And it's probably the most commonly used model, I would say, right? And the basic idea with an SIR model is you have a population and you assume that individuals in that population are in one of three states, or quite often we refer to them as compartments, right? And those three states are susceptible, infectious, or removed, right? So you start off in the susceptible state, which means you can get the disease, you haven't got it yet. And then there's some transmission rate that determines your risk of moving into the infectious period. Okay? Sorry, the infectious state. Usually the way we do that is we say we've got some transmission rate parameter, beta, or infectivity rate, it's sometimes called that. In our case, we're going to want to estimate. And then we multiply that by the number, this IT here, the number of infectious individuals, right? So the more infectious individuals there are at time t, the higher that rate is. And often we standardize this by dividing through by the population size. And we don't have to do that, but we often do. Okay, it's just in this case, it's just a scaling factor essentially. Now, if we're unfortunate enough to be infected, under this model, we immediately become infectious. So we can start passing on the disease as soon as we're infected. And then at some point, we enter this removed state R, right? And that occurs according to some removal rate, this gamma down here, which also determines the infectious period. So often we think of that in terms of 1 over gamma, which actually gives you the average infectious period, okay? And just to make clear before I move on, notationally, I'm going to use ST, IT, RT to represent the number of individuals in each of those compartments, susceptible, infectious, removed. You can set this up so that SI and R are the proportions, right? So here, S at any given point in time, S plus I plus R is going to equal N, the population size. I'm assuming there's no births, no deaths, no migration, right? But you could set it up so that this equals 1 and you track the proportions over time. And then one last thing that I wanted to say, so this R is often referred to as the recovered state. More generally, it's a removed state. What it means is you're essentially disconnected to the population in some sense, right? You can't infect anybody, you can't be infected. So it can mean you've recovered and you've acquired immunity, but it might mean you've died, it might mean you've gone into quarantine. Right. So more generally, we refer to this as a removed state rather than a recovered state. Okay. Now think about how individuals are going to pass through those states. It's very simple, I can write this down in terms of a set of difference equations. So the number of susceptibles at time t plus 1 is going to be the number of susceptibles at the current time point minus this IT star, which is going to be the number of new infections at time t, right? So IT star and RT star represent those new infections, new removals. Okay. Similarly, in terms of the number infectious at time t plus 1, well, that will equal the number currently infectious plus the new infections minus the new removals. Okay, and then they will pass into the removal state. And so the RT plus 1 will equal RT plus RT star. Okay. Now I want to set up some sort of stochastic mechanism that people get through this. I should say that actually, so a lot of the time when people model this, they use ordinary differential equations in continuous time. So all of that is deterministic, but we, being statisticians, are obviously going to have a stochastic model that can capture some of the uncertainty that we certainly see in disease data. Right. So all the stochasticity essentially happens on this slide. Right. If I think about the number of new infections, well, at a given time point, the maximum number of new infections I can have is going to be the number of susceptibles at time t. Okay. And then that's going to happen according to some probability, which I'm going to call here pi t si. And that's defined down here. Right. So that's basically, there's an underlying assumption of a Poisson contact process and homogeneous mixing. And what you end up with is an infection probability that looks like this. It's 1 minus e to the minus, and then that transmissibility or infectivity that I had on the previous slide, right? So beta, the infection rate, times the number of infectious individuals divided through by the population size, where actually that's optional. Okay, and then similarly, the number of new removals, well, that's going to be binomial as well. The maximum number I can have is the number currently infectious, right? Theoretically, all of them could enter the removal state at one time point. And then we have a probability determining that, which is just going to be 1 minus e to the minus gamma, right? So obviously your infectious period doesn't depend on who else is infectious or how many other individuals are infectious, but your risk of getting infection, becoming infectious does. Okay.
Rob, I have a question. I'm interrupting because I think it's an important question. Can you explain more these stochastic compartments?
So I'm guessing I answered that on this slide. Was there something more?
Rodrigue, please, you can type again if you have further doubt about about the interpretation of these compartments. Okay, but I will say that it has been answered. Okay, go ahead, Rob.
Okay. All right. And then if you simulate from a model like that, the number of susceptibles, infectious, removed, changes over time. The number of susceptibles will go down. The number of removed will go up. Generally, the number of infectious goes up and then down again, right? And if you want to go through this matrix and check that it fits those difference equations, you can do that afterwards. But it's a fairly simple calculation. In fact, you can do this in Excel if you want and run these things, and people do that. Not me. Okay, so graphically, what does this look like? So here I've got a population size of 10,000. I've set my transmission rate to be 0.8, my removal rate to be 0.2. So my infectious period here will be 1 over 0.2, which is 5. Okay, and it's generally this red curve that we're interested in, the number infectious, or sometimes we look at the number of new infections, right? But that tends to go up. And then as my number of susceptibles goes down, you reach an inflection, point, right? There are fewer and fewer susceptibles to be infected. So this curve heads back down until pretty much everybody's been infected, right? This is stochastic, so the epidemic can die out early. So it's not necessary that everybody gets infected. And actually, you can see that the number of infections which goes to 0 is lower than the number of susceptibles. So there are still some susceptibles at the end of this simulation here. Okay, and similarly, or not similarly, it's the inverse, right? But the number of removals goes up over time and tends to go to n, depending on when the epidemic dies out. Okay, but there is stochasticity in here. So here's a graph of 20 epidemics. So you can see I've actually changed the infectious period here. I've halved it. So this is peaking much lower. Previously, it was peaking around just over 4,000, 4,500. These peak generally around 400. Okay, but there's a fair amount of variability there. And you can actually see there's at least one curve down here where the epidemic died out through random chance at the beginning and never got going. Okay, so there's a probability of not quite 0, but low numbers of infections as well occurring. All right, so that's I can see that there's no questions there. I'm just going to talk briefly about inference for this model. Okay. So the likelihood for this model is actually very simple. In fact, let's go back to this stochastic slide, because everything really interesting going on is occurring here, right? I've got a bunch of new infections at each time point, so a time series of new infections. I've got a bunch of new removals at each time point, so a time series of those, and they follow binomial distributions. So I can just write down the binomial mass functions, and this is actually where we come. How did that happen? This is the log likelihood, so it's all on the log scale. But if you look at that, you'll see that that's just binomial mass functions on the log scale. Okay, so if you know the number of infections at each time point, or new infections, and you know the number of new removals at each time point, you plug that in to this likelihood, and you can maximize that quite easily to do maximum likelihood inference. Okay, using the optim command in R or however you like. And in fact, there are packages around, R packages around to do that as well. Okay, so actually, I will answer this question as well just before we go on. So the deterministic model, or the deterministic equivalent of this model, would be a series of ordinary differential equations, okay, which will look very similar. You've got the susceptibles being depleted by a rate given here. But you do this in ordinary differential equations. So the deterministic model, when you run that, you get the same output each time. And when I say deterministic, it's generally a continuous time version of that model as well, because it's an ordinary differential equations. That's the sort of standard SIR and the model that most people mean when they refer to as an SIR model. And actually, the deterministic model is great if you're just interested in the mean behavior. As you saw from this, I think the stochasticity that you get with these models is much more realistic of what we see in real life, right? Epidemics can die out. I mean, and, you know, just through random's a dangerous word, right? But unobserved or random things going on in the population, you can get quite different outcomes. So I think most people agree that adding some stochasticity to these models is a plus. And certainly from a statistical point of view, if you want to capture uncertainty, you have to do that, right? Okay, the vaccination question I will come back to later because that fits in better with the extensions. Please, Alex, remind me if I forget to address that. Okay.
Done.
Okay. So like I say, we can do maximum likelihood inference. We tend not to, right? We tend in this field to use Bayesian models or work in the Bayesian framework. There are a number of reasons for this. The first one there, that inference based on the posterior is highly interpretable, is perhaps not the most important one from a disease modeler's point of view, but is very nice, right? The fact that your posterior is probability distribution and you don't have to think about repeated sampling. What does repeated sampling mean anyway with an epidemic which only occurs once, right? Is very nice, right? But it's actually the second and third points here that I think are more important from a practical point of view, right? So one of the things is that I've said, if you've observed your number of new infections and the number of new removals at each time point, we can do maximum likelihood inference here very simply. Well, that actually is quite a big assumption, right? And generally, our epidemic data are incomplete in some way, often due to censoring, right? I do not normally observe when someone gets infected. I might observe when there's a lab diagnosis or when symptoms occur, but that happens after infection, and I may well not know how long after, right? And it can vary a lot between people, right? COVID was a very highly variable disease, right? So because of that, we often want to impute the data, or if you like, jointly estimate the missing data and the model parameters, which is conceptually straightforward to do in the Bayesian framework because the data and the parameters are both random variables or realizations of random variables. Okay, that's called data augmentation. And essentially, as I say, it means jointly estimating the data or the distribution, the posterior distribution of the missing data and the model parameters. Okay? It's harder to do in the maximum likelihood estimate frame. You could do it with an EM algorithm, but maximizing those high dimensional likelihoods can be difficult. And then the third one, and this is tied to the second point here, is the Bayesian framework obviously builds on prior information. Right? You start with your prior, you update that information with your likelihood. Well, in our case, we often have prior information because other people have done studies. As I said before, the parameters tend to be interpretable on their own. So you may have piecemeal studies. It's often quite easy to sit down with an expert and say, give me a 90 or 95% probability interval for the infectious period or the mean infectious period. What do you think is going to be the case? And the truth is, if you're doing this, where you're essentially trying to model the data or part of the data as well as the parameters, we often rely on that prior knowledge to put us in an area of the parameter space, or if you like, cut off unrealistic areas of the parameter space. And it aids identifiability of the models. Now, having said all of that, I'm not going to do this today. We're going to assume that we've seen we know the number infectious at each time point and the number removed. But just to bear in mind that we often do want to be doing that. Okay. All right. So in our case, there's our likelihood again. If we're doing it in a Bayesian framework, we put priors on our parameters. Our two parameters, beta and gamma, are both positive. They're rate parameters, right? So typically we'd use a gamma prior. You could use a half normal or a uniform, or a half t, something like that. And also often we will put the prior on the inverse of the gamma, the mean infectious period, partly because it's easier to elicit prior information that way, partly because it's just easier to interpret, right, from our own point of view. But you can do it either way. Okay. Now, the way we've been doing this recently in my group is using what's called Nimble. So Nimble is an R package, well, essentially a language for fitting statistical models in the Bayesian framework using Markov chain Monte Carlo predominantly, right? It has a few advantages. So it's built upon these older languages, so bugs and JAGs, and you can do everything today, everything I'm talking about today, you can do using bugs or JAGs. But Nimble's built on that, which means there's a lot of material out there. If you're learning Nimble, you can get code for all different sorts of modeling situations. But the key thing here is, or one of the key things is that Nimble compiles the MCMC in C++, which means you end up with pretty fast MCMC algorithms, which can be an issue for complex models or a lot of data augmentation. And then the other thing that I can't really get into today is that Nimble also allows us a lot of flexibility. So basically you can go into Nimble and change the MCMC proposals, samplers that are being used for different parameters to make things more efficient. That becomes important when we do data augmentation. Okay. Now, I don't have time really to go through all the Nimble code, but I have a markdown file. So if I can close, I know how to use my own computer. There we go. If I go to my web page, so the link for my web page is at the beginning of the slides and on the final slide as well. If you just search for Rob Dearden, you may have trouble finding this web page because it's a new one. I had a University of Calgary one, and then, well, they got rid of their web hosting, and so I've got a new GitHub-based page. But if you scroll, as you can see, I've got a picture of me there that when I was quite a bit younger. If you go down to the bottom of the opening page, you'll see that there's our Nimble code bit for today's talk. The markdown file is there. If I click on the PDF, that will download, and I'll just briefly show you what's in this. So I'm going to go through this very quickly. We've got a bit of code here which basically defines the model. Right? If you take a look at this, this is setting the initial conditions, and then this has got the removal probability, the infection probability. This one changes over time. This one doesn't. The new infections, the removal infections, so that's the key part of the model. And then also what this is as well, the updating of those things. So this is the difference equations, and then my information about the priors. And then we do things using this model, right? So on the next couple of pages, we do some simulation work. So you can see similar things to what I showed you in those slides. And then here, well, I've got slides on this in the talk, but this is basically the code for simulating a data set, specifying my prior, and then using MCMC to fit that model. Okay. Now, apologies that that's so quick. I don't really have time to talk about it now, but please feel free to have a look at that afterwards. And if you have questions, let me know. Oh, I should have said. So Caitlin Ward, who's now at Minnesota, but was a postdoc of Alex and mine, she actually coded most of this up. So really those author names should be reversed. I mean, I did make some changes, but Caitlin did most of the work, learning how to code these things up in Nimble. Okay, so she needs a big dose of credit there. Okay, so there's all the code in the background. We'll forget about that for now. What I've done here is simulated a data set. So with the transmission rate of 0.6 and the removal rate of 0.2, so my infectious period once again is 5 days. And here what I've got is the number of new cases, so it's called this incidence, number of new infections shown by this curve, and the number of new removals, which is obviously delayed a little bit. And then that data set, which is essentially 2 time series, right? If I want to analyze that, I need to put a prior on it, or priors on my parameters. Here, what I've done is I've used an exponential prior, so a gamma prior with rate and shape equal to 1 for beta. Okay, so if you remember, my true value of beta was 0.6, so this is a pretty uninformative prior on that beta parameter. On the gamma, I can do this analysis with a non-informative prior on gamma as well, but what I've chosen to do is pick a prior that essentially has sort of ties to information we might have in real life. Right? So I've picked this prior so that essentially that's about 1/6, that's about 1/4. So about 90% of my prior mass gives me a mean infectious period between 6 days and 4 days. Okay, so that's the sort of information you get. And if you want, there are packages that will elicit these priors for, given quantiles like that. So like I say, this is a reasonably informative prior, but not that informative, actually. If you simulate data with a 4-day infectious period and a 6-day infectious period, you actually tend to get quite different looking epidemic curves. Okay. I'm supposed to be leaving this to you, Alex, aren't I? I'll come back to these questions in a minute.
Okay, just let me know. I'm here to help you.
I know. This is my control freakery. Okay. So if I run my MCMC, what do I get at the end for that data set? Well, I get my MCMC trace plots. For those of you who aren't familiar with MCMC, what I'm essentially looking for is stationary curves, right? Or stationary plots. Because what MCMC does is it sets off a Markov chain, which when it reaches stationarity is exploring the posterior, right? So if I throw away some of this curve, it's not really a curve, is it? It's chain, that's the word I'm after. Throw away some of this chain, I can treat the rest of the chain as if it's a sample from the posterior. And then that's what I've done down here. I threw away 1,000 samples from those chains. So I get my marginal posterior for beta. Remember, the true value was 0.6 here, and I get my marginal posterior for gamma. My true value was 0.2. Okay. All right. I should say that these trace plots are beautiful trace plots. That's really because we have simulated data. It tends to be a little bit harder to reach stationarity with real data when you've got, problems with fit. And then I can do things like, just find the posterior mean. So it's 0.6, well, to 2 decimal places, 0.61 for beta, 0.19, well, 0.20 for gamma, so very close to the true values. And I can get my credible intervals. So here I've just got percentile intervals, the 2.5 and 97.5th percentiles of my posterior, which are obviously capturing the true values. Okay. All right. So that's my brief overview on how to fit that sort of model to data. As I say, you really will need to dive into the Nimble a bit more to understand what I've done, but it is easy to just code up the likelihood and maximize it in R. Okay, so a couple of questions. Can models like these be used to model situations where infection is considered a social influence? Okay. I don't understand that question. Okay.
So let me just suggest, John, that you clarify the question, please, and then Rob will address it again.
Yeah, there may be different language in different fields, but I don't quite follow there. And as for books, well, I'll come on to that in in a few minutes. Okay. All right. So one sort of aside I'll go through quite quickly. I want to talk about this idea of a basic reproduction number, or R naught. This is essentially a statistic or a quantity that's used a lot in infectious disease modeling. It's known as R naught or R0. And what it represents is the expected number of infections that result directly, so directly is important, from a single infection in an otherwise wholly susceptible population, right? So it's conceptually, we're saying, here's my population, one individual gets infected somehow. How many individuals on average do they directly infect, right? And it's a useful metric because neither the transmission rate or the infectious period on their own really tell you about the strength of the epidemic, right? A very large transmission rate but tiny infectious period might not give you a very strong epidemic. Right? Now, it turns out if you go through the math, it's very simple to calculate. In an SIR model, it's just the transmission rate divided by the removal rate, which is what the transmission rate multiplied by the infectious period, which conceptually sounds completely correct, right? Well, it is completely correct. The transmission rate determines how often you are infecting. The infectious period determines how long you're infecting for, okay? And it captures, if you like, the strength of the epidemic. It has this nice threshold behavior in relation to R naught equals 1. Right? So it turns out that if R naught is less than 1, the epidemic, if R naught is greater than 1, start there, that means on average, you're infecting more than one individual. The epidemic tends to take off and infect the entire population. Okay. If it's close to 1, it could die out through random chance, but it tends to go through the whole population. Whereas if R naught can be brought under 1 or is less than 1, the epidemic will tend to die out. Okay. And that's one of the reasons it's of interest. We don't really need to, well, it's here now, right? So here's a couple of examples. So if I had a situation where beta equals 1, gamma equals 0.2, so my R naught equals 5, I get a curve here that looks like this. I've done this on the proportion scale over here. So that's the proportion of the population susceptible, infected, or removed. If I halve my transmission rate, right, but I keep the removal rate the same, my R naught goes down by half as well, 2.5. You can see what happens is I end up with a much slower epidemic. Okay? And you'll remember from COVID at the beginning, there was a lot of talk of bringing down the R number so that we had more time. The epidemic was slower. We had more time to put in place, you know, emergency hospitals and public health measures and that sort of thing. Okay. But often what we're trying to do is bring that R naught right under 1 so that we can actually get rid of our epidemic, right? So that it dies out. Okay. Okay, let's okay. So the question about the social influence question is, I would say yes, but I don't know enough about the field. Like I said, people do use these sorts of models because the more the more you see a social media meme, or the more people who see a social media meme, the more there are to pass that on. So the general numbers of people who see a social media meme or do something like the ice bucket challenge could follow that sort of the similar sorts of dynamics. Okay, thanks for clarifying that, John. Okay, how are we doing? Well, I'm going a little bit slow, but I do want to talk a bit about some of these extensions. Okay, I'm going to go over these quickly because really I've just introduced you to the classic disease model, but there are lots of different possibilities. Right? So one of the possibilities is to change that compartmental framework, or the number and types of states, right? So I said before, and then corrected myself, that the SIR was the simplest non-trivial model. Probably the simplest non-trivial model is the SI model. So in the SI model, you essentially allow for infection, but then assume everybody stays infectious for the rest of the time period you're observing. Okay, that can be useful. I mean, some diseases people don't recover. If you're looking over a fairly short time period and then modeling something with an infectious period that's long, HIV is the obvious thing that springs to mind. An SI model might make more sense than an SIR model. Okay. The other thing that's very common is this SEIR model that I will talk a little bit more on the next couple of slides. That basically allows for a latent period where, after getting the disease, your body is reproducing the virus, the bacteria, the pathogen inside you. There's a time at which you don't have enough of that pathogen to infect other individuals. So you go through this period, exposed period, we refer to it, where you're infected but not yet infectious. Okay, that's in a lot of diseases, that's a very important thing to include. And then another sort of class of these things are models that allow for reinfection. So SIS, SIRS, SEIRS, right? Where after your R state here does mean recovery with immunity, but that immunity dies off after some period, and so you go back to being susceptible, right? So what you'd essentially have is, if you remember, I had that initial flow diagram with my rates, there would be another rate, let's call it lambda, at which individuals go back to being susceptible, for example. Okay, and you can build up the model quite simply in that way to make these things quite complex. Okay, so just to show you how simple that is in terms of an SEIR model, which is one of the simplest models. So I put in this extra compartment there. Individuals would get infected at the same rate as before, right? So the rate of infection depends on the number infectious, doesn't depend on the number exposed, obviously, because they can't infect yet. And then movement from exposure to or exposed to infectious, that just occurs according to some rate, in a similar way that the movement from infectious to removal occurs, right? So you end up with an extra line in our difference equations, an extra probability, an extra binomial mass function that we plug into the likelihood, right? But if you've observed these three time series, the number of new exposed, the number of new infectious, the number of new removed, this model perfectly easy to fit. Okay. Another thing that's very common in these models that I'll just briefly touch on is to make your transmission rate time vary. Right? So all I've done here on this slide, if you look at the previous slide, of this transmission rate here depending on beta times I over n. I've just put a t there to emphasize that that beta t may change over time. Now, why might that change over time? Well, beta in this model is capturing really two things. It's capturing the strength of the pathogen, or how infectious the pathogen is. How easily does it get into your body? But it's also capturing the contact rate in the population. They're both included in that one parameter. You can separate them out, but we haven't done that here. Okay, so the contact rate, that can definitely change over time, right? People can react to a disease being in the population. Governments can bring in restrictions. So actually can the strength of the pathogen, right? If a pathogen is evolving, that may change as well. You can model this changing transmissibility in all sorts of ways. You can have a linear trend or something more flexible. A very common thing to do is just allow for change points, right? So this is a graph of new cases of Ebola virus from Sierra Leone in 2014, 2015. So the curve here follows a very typical shape for an epidemic curve. But you can see these two red lines. And I should say, like, for those of you who aren't aware, Ebola is a devastating disease. It has a very high mortality rate and the symptoms are like horrible. So there were two red bars here, which basically show changes in government policy, essentially, right? So this UNMIR was a UN-initiated policy, which was introduced at the beginning of October to essentially make sure that cases were isolated and safe burials were carried out, right? So that infection from newly infected individuals were less likely to infect others. It actually took a few months before they felt like they'd reached 100% case isolation and safe burials. So what you could do, and what was very common, is to model your transmissibility so that at some rate at this point changes after the UNMIR policy comes in, and maybe changes again after the 100% case isolation is reached. Okay, so writing down that model is very simple. Okay, we just allow our beta t to be one value before the time period change, and I meant to mark this on here, so that I'll call that T1 star and call that T2 star. So we have a transmission rate before the UNMIR comes in. We have a transmission rate afterwards, but before 100% effectiveness is reached, or they call it 100% effectiveness. I imagine in reality it's close to 100% effectiveness. And then a further change in that transmission rate, represented here by the beta 2 after that time period. Right? So that's also a very common thing that's done with these models. Okay, so that's all I wanted to say on the population level models. I would say, unfortunately, that there's no book that sort of covers what I've talked about so far in one place, right? But there is a lot of stuff out there. So a nice book, relatively new book by Bjornstad called Epidemics and Models and Data Using R gives a really nice overview of these population level models. I think they call them time series SIR, right? So time series SIR is often used to mean what I call discrete time SIR. I believe, I should have checked this before the talk, I believe that they talk about this mainly in the maximum likelihood framework rather than the Bayesian framework, but that might not be right. But it's a really nice book, okay? If I skip down here, there's a more advanced book, one of those Chapman and Hall Handbook of Infectious Disease Data Analysis books by Leonhard Held and others. It covers a very wide range of different modeling techniques. It doesn't tend to give you the code. It goes more into the, the math and how these models are used. And then the other thing here is if you are really interested in Nimble, there can be a little bit of a learning curve with Nimble, but the Nimble user language, which you can find either on CRAM or on the R site, is really nice. It's got a tutorial, and there are actual tutorials on YouTube and all of that sort of thing as well. So these are the three things that I would start with. Okay. If you're new to Bayesian modeling, then I do believe there's a talk. One of these talks is up on the community, the ASA community website. So I would go there and start there. Okay. Okay. So I'm fairly new to compartmental models. How do we approach multiple strains? So that's a little bit more complicated. So I have done a little bit of work in that area. The usual way is to build into your model an assumption that if you get one strain, you get full protection from that and possibly partial protection from the other strain. And then you can do that either by changing the transmission rate or by changing the infectious period is another way of doing it. It's a little bit more complex, or too complex to go into today, I would say. But if you send me an email, I can point you to some references. Okay. David asked, how do you communicate the stochasticity in the models? Can we say anything definitive about the probability of some number of infections being exceeded? Yes, you can. And that's one of the nice things about the Bayesian approach, right? I can get my posterior distribution. I can simulate, like draw parameter values from that posterior and simulate epidemics and do that over and over again. And then my epidemics that I simulate, or my epidemic curves, capture that uncertainty. I can then do whatever I like, right? I can look at the probability, the number of epidemics in which the peak was above some level, or in which the number of infections were above some level. Okay, so that's actually a really nice thing to do here, and it is key, probably, to communicating stochasticity. I find actually public health, well, maybe it's the people I deal with, but a lot of public health people are better at understanding stochasticity than statisticians give them credit for, right? Visually, or turning it into some epidemiologically important metric, like the probability of a serious epidemic, I think is key to doing that. Yes. Okay. And then Anonymous had a question. In a population where the disease under study is vaccine presentable, would you still include the vaccinated subpopulation, or rather consider everyone to be susceptible? So it depends, right? There are diseases where it's pretty safe to so you may allow in your model those individuals to go straight to being removed, right? Or you can allow for different levels of infectivity, right? So you could have a situation where you have S, I'll call this I1 and I2, right? And those different I compartments might represent vaccinated individuals, unvaccinated individuals. So we know in COVID, right, that the vaccine was not 100% effective. People could still get it and they could still pass it on, but probably at a lower rate, right? So this sort of framework would allow for that. Another thing that was often done in COVID, which I haven't mentioned, is I have a situation where you have asymptomatic cases and infectious cases. So these would be individuals who have COVID but don't have any symptoms. And obviously the Bayesian framework is nice for that, because you need to impute this number, because we don't know how many asymptomatic cases there would be, right? But if you sit down, you look at your flow diagram, you think about the rates, it's very easy to build these models up into more complex models. Of course, if you do carry on doing that, it gets harder to parameterize them, right? The more complex the model, the harder it is to find information on those parameters. But that's a ubiquitous thing in modeling and statistics. Okay, so I think I got the questions. All right, so I'll try and go through this quickly, but I'll just briefly talk about a different approach. Well, it's not really a different approach, it's an extension of these models, but perhaps it starts in a different place. Okay, so in our classical SIR model, I essentially had this situation, right? I was essentially assuming that the infection rate per individual is the same for every individual at a given time point, right? So my individual infectious rate, if I think about that, beta IT, where I is your individual, is just equal to beta T, and that's proportional to some parameter multiplied by the number of infectious individuals, right? I say proportional because we divide through by n. And we've also got this homogeneous assumption, right? We've got this assumption that people are mixing homogeneously, completely at random, and we're assuming they're all the same. Okay? Now we know real life is not like that. Okay, you can think of lots of factors that are going to affect your risk of getting the disease or passing on a disease. Geography is an obvious one. I am more likely to contract a disease from people in my neighborhood than I am from people who live in a city 3 hours drive from me, right? And actually, you can think about geography or spatial distance. Human diseases are often better modeled through contact networks, right? There are a bunch of individuals I come into contact with, people I live with, people I work with, maybe people who live in my neighborhood. They would all occur at different rates, and you can represent that sort of contact through a contact network, right? A graph where this describes individuals, and then you have edges describing whether people come into contact or not, right? And that can represent all sorts of different types of contact that I'll talk about in a minute. Genetics may affect your susceptibility to a disease. Immunity, have you had the disease before? Have you been vaccinated before? Have you had similar diseases, right? Different strains of the same disease, that may all affect it. Things like lifestyle factors, environmental factors, they're probably tied to immunity, right? They may affect your immune system. Well, lifestyle factors may also affect how likely you are to pass on the disease as well. If you're using intravenous drugs, there's a risk factor that you have for passing on a disease as well as getting a disease that you may not share with people who don't use intravenous drugs. Okay, so as part of my postdoc that I did, what feels like 50 odd years ago now, I worked on a modeling framework for these sorts of situations. We called it individual level, other people call it individual based. You can get more details about that framework in this Statistica Sinica paper if you're interested, although there are easier ways of getting into it. But I'll talk briefly about that framework. Right? So what might we want to go into those models? What characteristics are going to be important? So one set of characteristics that you might refer to as susceptibility are risk factors associated with you getting the disease. Okay, so they could be things like age, could be things like genetics, could be environmental conditions, could be whether you were vaccinated, could be your infection history, right? And lots of other things we could write down. Okay. There are also going to be risk factors possibly affected that affect your chances of passing on the disease if you have it, right? And we refer to those as transmissibility risk factors, your risk of transmitting the disease. And you can see here that I've written essentially the same, well, not essentially, exactly the same risk factors, because they may be the same. They may not, right? We can use the model to find that out. But I may be more likely to get the disease if I'm a certain age. I may be more likely to pass on the disease if I'm a certain age, and they may not be the same ages. Right? Similarly, if you think about COVID, say, whether you've been vaccinated, you might think that's going to affect your susceptibility most, and probably it does, but it may affect your likelihood of transmitting the disease. If you've been vaccinated and you produce less pathogen, you're probably less likely to pass it on. On the other hand, if you've been vaccinated and so then you're very confident about your own protection, you may be more likely to come into contact with people. So it could go either way, right? So there are two things, what we call susceptibility and transmissibility. And then there's another issue of connectivity. Okay? How far apart are particular susceptible and infectious individuals? And we normally model that in one of two ways, or possibly both. We look at spatial separation. So there may be Euclidean distance, it may be the road distance between individuals, or network-based separation. Are you connected in a network? And if you're not, how closely are you connected in a network? Okay. And then the sort of modeling framework that we wrote down for that paper looked like this. Right? So now I've got my beta IT, which is the infection rate of a susceptible individual I at a given point in time. I've missed out that time t, haven't I? Okay, and this works in continuous or discrete time. And well, I've got something that certainly looks more complicated before, but it's actually very similar to those characteristics I just described, right? First off, I'm going to have a susceptibility function for individual I. So that may have those susceptibility risk factors, you know, age, gender, whatever it is. I've then got this, I multiply that by this term in parentheses that we often refer to as infectious pressure. Right? And this sort of does the job that the number of infections was doing in the simple SIR model, but it's more complex, right? So here what I'm doing is I'm looking at the set of infectious individuals at time t, right? So IT here is a set, should be a curly IT actually to differentiate it. It's a set, it's not the number. And then for each of those, I'm going to have a transmissibility function. So this is with subscript J now. And I'm going to have what we call an infection kernel, could just call it an infection function, right, which describes the connectivity between individual I who's susceptible and individual J who's infectious. And then we sum over all of those. And then what we also tend to do, I didn't talk about this before, is we add on a bit of random noise, right? So we have this epsilon function here. Here I've said that it with a subscript I, so it can vary between individuals, can depend on covariates, and it can change over time. Often we just make this a constant, right? But that random sparks function allows for infection coming in from outside the area you're looking at, right? So if I've got say I'm doing a spatial model that I'll talk about, I've got individuals that I'm looking at, I have data on those individuals. Well, there may be infections from outside, I just don't observe those, right? Maybe they're in a different jurisdiction, but they can still infect, right? So having this term, this random sparks, allows for infections that the main part of the model here can't otherwise describe. Okay? And like I say, we often make it a constant. Sometimes you may make it follow, like multiply it by the total number of infections, so it follows the general strength of the epidemic. And then finally, put that in a big square because that's important. If I want to put this in a discrete time framework, I have something that looks similar to what we had before. So the probability that a susceptible individual I is infected at discrete time point t is just 1 minus e to the minus beta, where beta is this thing. Okay. The big difference is this is now different for every individual, potentially, in the population at a given time point. In terms of the infectious periods, generally we model that in the same way as before. We just assume that individuals recover at some rate, which defines an infectious period. But you could, if you wanted, make the infectious period also depend on covariates. We don't tend to do that so much. Okay, so what I'll do is I'll just show you a couple of quick examples. These are very simple examples. So here what I've got is I've taken my beta IT. I've essentially set my susceptibility function to a baseline, alpha, I've called it. So I'm assuming there's no covariates. I've done the same thing with the transmissibility, but for identifiability reasons, I just set that equal to 1, right? Obviously, you can reverse those two. So basically, I've got no covariates, is what I'm saying here. Okay. Except what I'm going to do is say that the connectivity in my population, my kappa ij, is going to be d to the minus delta, right? So dij there is going to be the distance between individuals I and j, I the susceptible, j the infectious, and then we raise that to some power where delta is a positive value, okay? So this model, everything's purely spatial. The power law kernel, that spatial kernel, is going to look something like this for different values of beta. So as the distance between individuals increases, the risk of infection goes down. And if I say simulate, and here what I've done is I've simulated across a grid of individuals, right? So you could think of this as crops in a field, if you like. We started off with some infection in the middle there. The red there is going to be my infectious individuals. The black are going to be my removed. And what you see is you get this sort of wave-like progression at each increasing time point, but it's a very messy wave, right? Infections are more likely to occur close by, but they can go over a reasonable distance until you end up with, I'm not quite sure when that happens here, it might be time point 13, time point 11, that everybody has been infected. Actually, it's not, is it? I can see some just about there. So time point 12 or 13, everyone's infected. Right? But obviously I can put covariates in there as well if there were covariates determining risk of susceptibility or transmissibility as well. If we change tack and now think about a network, so all I've done here is I've replaced that kernel, d to the minus delta, with Cij. And what's Cij going to be? That here is just going to be a 1 if I and j have contact, and a 0 otherwise, right? So what does have contact mean? That means any sort of contact through which the disease could pass, right? So depending on the disease, that may be, are you sexual partners? Do you live in the same house? Is this person in your social network? If we were modeling farm animal infection, it might be, does your farm share a supplier with the other farm, something like that? Or are you in the same field, right? Those sorts of things. So that would represent some sort of contact network that looks like this. So this is for 100 individuals. You can see the way that we've simulated this. We've got individuals in the middle that are highly connected, so at high risk of infection. We've got individuals that only have 1 or 2 connections that are at lower risk. And actually we had a couple over here who are completely separated. So under this model, unless we had a Sparks term, those 2 individuals labeled 64 and 7 couldn't be infected, right? But under this model, the disease would pass through that network. And we can do things like throw in lots of different networks, right? So we could have a whole bunch of different networks representing domestic connectedness. Do you live in the same house? Do you live in the same region? Do you work in the same building? All sorts of things to make these things more complicated. The way I set it up here, we actually have a series of binary networks. They don't have to be binary. We could weight these networks, right? So I could put a weight on these edges that represent different risks of spread, okay, different likelihoods of spread. And I could make them directional, right? So I could make it so that it's 0.8 going that way and 0.4 going the other way. So maybe individual 96 is more likely to infect individual 16. And so you'd want some different weighting there. So you can make these things much more complicated. This slide, this is not from one of my papers, but it just shows briefly or gives you an idea of the sort of thing you can do. Right, so this comes from a study by Simon Kaushemez et al. It was from a Pennsylvania elementary school, quite a small school. And they went in and basically talked about to the kids, each of these nodes is representing a child, and the edges are representing essentially, are those children friends, right? So, or did they say that they were friends? There's actually direction in here, I think, representing that. And so you've got this network, a social network, essentially. you've got more information. We've got the color here is showing the gender. So you can see a lot of gender clustering, apart from this guy over here who likes to play with the girls. We've also got, I was that kid actually. And then we've also got shapes here that show the different classes that these children were in. So you could throw gender and the class in as susceptibility and transmissibility covariates, and then the network would go in as the kernel. And what they did was they used this essentially as covariates for a model, modeling the spread of H1N1 influenza from 2009, right? What was known as swine flu, but we shouldn't really call swine flu. Okay, so these things can get quite complicated. This slide I'm not going to really talk about. This is actually from that Statistica Sinica paper. I've just put this in there to show that things can be quite complicated, right? You can have susceptibility covariates, transmissibility covariates. You can make it non-linear. And actually here, what I've got is a spatial kernel where we have a continuous risk of infection up to some change point, which in this case was supposed to represent contiguous or adjacent farm spread, and then some power law after that point, right, where we would estimate this change point. Okay. So you can make these things complicated. You can make it much more complicated than this, actually. Okay, I really am running out of time, but I will spend a couple of minutes on this slide if it's okay. The likelihood for this sort of model is very simple to write down. Okay, it looks like this. It's basically got two main components. Over here, I've got a component for my infectious period. Right? So I'm going to use this delta J here. I'm going to say that's my infectious period for the individual J which got infected. I allow that to follow some distribution. Geometric is common. You could use Poisson or negative binomial. It's essentially, it's equivalent to modeling removal in the way that we did before. Okay? But this is the way we tend to do it in these models. And then over here, I've basically got the infections that are occurring. Right? And if you think what happens at any given time point, either you have an individual that was susceptible at time t, who remains susceptible at time t plus 1, and they're infected with probability 1 minus PIT. Okay. Or you get an individual that is infectious at time t plus 1, but wasn't infectious at time t, so this is newly infectious. This is like our I star from before. And that happens at time with probability P. And then we take the product over all time, right? So the likelihood is very conceptually simple. It's like a heterogeneous Bernoulli-based likelihood, and then a component for the infectious period. However, it can be very computationally cumbersome. Right? If you've got a large population, you have a large amount of probabilities to compute, which will differ between individuals and change whenever there's an infection or a removal. Okay, so there's a lot of computation there. And if you think about sort of these spatial models, each of those PITs has this summation with this nonlinear term in it as well. So if you code this up in an inefficient way, well, let's put it this way, it's very easy to make this inefficient. And for large populations, if you're doing MCMC, it can be very, very slow. That said, and this is my final slide, we actually have 2 R packages for modeling at the individual level. And each of those has a vignette, a paper associated with them. The one that we've talked about today or that's relevant to what we've talked about today is a package for modeling in discrete time. It's called EpiILM. There is a paper that basically takes you through, shows you how to simulate. I've got it here actually, shows you how to, well, there's the model, gives you the the basic functions there, talks about how to simulate, where's my plot gone? All right, well, simulate spatial models, simulate network models. There was the plot I was after. This is it's got some graphics commands for doing this plotting. And then there's a network example. And then finally, it's got all the information you need to fit these models using MCMC. Okay, so I know obviously this is my paper, but I think it's a really good introduction to these sorts of models and how to fit them. Okay, there is also, we haven't talked about this at all, but you can do the equivalent thing in continuous time as well. And that's all detailed in this package. Okay. All right. So it's 11:28 by my time. So I'm just about within the 90 minutes, but I can stay on to answer questions if you would like. I do see one in the Q&A. So is it possible to apply this model to an RCT study? If it's not possible, what is the correct way? So an RCT study I assume you mean there's some sort of intervention in the community. Well, there's different types, right? In the livestock industry or veterinary research, they do, and crop research as well. They'll actually, have controlled infections. And then, yes, quite often we would use these models to either, trying to get in a crop trial, it might be the extent of the spatial spread, or there might be treatments that we're trying to ascertain their effectiveness. You can also do RCTs in the community so we worked, for example, a few years ago on Hong Kong, influenza in Hong Kong. And they were trying to look at the effect of vaccinating children in houses. So they had a bunch of houses where they vaccinated the children, or one child, I think it was, and looked at the probability of the other inhabitants getting infected versus control houses where there was no vaccination. And so, yeah, you can apply these sorts of models there as well. The community model is much more complex, or it's not that it's more complex, it's much more noisy, because in influenza season, you're obviously not observing the whole population and you've got a lot of other things going on. But yes. So thank you. Samuel, no, you didn't miss something. I skipped over completely the priors. It's essentially in the same way as before, because the priors for these models we tend to constrain them to be positive. So for example, here, the parameters would definitely be positive. So the usual thing is to put a gamma prior on them, or a half normal or something. If you've got, it tends to be harder to get informative priors on things like the spatial parameter, especially as now when you fit these models, you do tend to see quite a bit of correlation between these parameters. So it's a little harder to do prior elicitation. So often we try to aim for non-informative or weakly informative priors. But no, all that I talked about before does apply, right? And in the packages, we have 3 or 4 different prior distributions you can use, and you have flexibility to choose the prior parameters there.
Just before you, okay, this is what I was going to address. Carolina will tell you about the next webinar before I thank Rob and this session. Carolina, please go ahead.
Yes, so thank you so much to Rob for a wonderful webinar. I'm also excited about the next webinar. It will be an overview of some methods for statistical analysis with missing data. And it will be taught by Rod Liddell from University of Michigan. He's one of the world's leading authorities in missing data. So it should be another great one. So I hope you can join us. Also, as Alex said at the beginning, we'd like to encourage you to join ASA and to thank ASA for making events like this possible. There's a new membership fee for developing countries, which was reduced substantially to just $10. So just a reminder, and we put some links on the chat for the new talk, as well as earlier for the membership information. Okay, so I'll hand it back over to Alex.
I've seen Rod Little talk on this subject as well. He's an excellent speaker, and I'd highly recommend that seminar.
Well, I have to say that there are many messages in the chat thanking you, Rob. And again, I just would like to thank you for sharing with us your expertise on the modeling of infectious diseases. It was really nice. I would like to remind the participants that the slides and the recording will be available from the SIRS website. The website was posted in the chat. And as Carolina said, we encourage you to become a member of the American Statistical Association. This initiative wouldn't be possible without the ASA support. And again, this is a webinar that is organized by the Committee on International Relations in Statistics and Statistics Without Borders. And we hope to see you on September 20th. And if you do have suggestions of topics that would be interesting for us to consider, please don't hesitate to reach out to Sloka, Carolina, or myself, or Donna, and we will be happy to try and bring this topic. Yeah, I think that's it. Thank you, and good afternoon, good evening, wherever you are in the world. We saw that there were people from all over, as it has been happening in previous editions of the webinar. So see you soon, hopefully on September 20th. Take care. Rob, thank you again. Thanks a lot.
No problem.